All right, what if you could literally architect a landscape, not with dirt and shovels, but with pure math? That's kind of what we're doing today. We're going to dive into higher order derivatives, and our guide is Chapter 3 of the legendary textbook Vector Calculus by Marsden and Dromba. We're going to see exactly how mathematicians can map out peaks, valleys, and even those tricky mountain passes in any dimension you can imagine. So let's start with something you might see every day. How does your GPS, or maybe a fancy mapping drone, find the absolute highest point in a massive mountain range? I mean, think about it. It can't just go and measure every single inch of ground, right? No way. It has to be smarter. It has to understand the shape of the land. And that right there is a classic optimization problem. And trust me, it's way more complex than it sounds. Well, in mathematics, this whole challenge has a name. It's called finding the extrema. The ultimate highs and the ultimate lows. And the essential toolkit for doing this? It comes straight out of Chapter 3 of Marsden and Dromba's Vector Calculus. And this book is famous for a reason. It's all about connecting these really abstract ideas to how the world actually works. Okay, so here's our game plan for today. First up, we're going to push our thinking into a new dimension. Then we'll get the tools to actually map out its curvature. Once we've got our maps, we'll use them to pinpoint all the peaks and valleys. And then, the really cool part, we'll see how this connects to the fundamental laws of physics. And finally, we'll see how this whole chapter is basically the launchpad for the rest of vector calculus. All right, let's jump right in. Section 1, a new dimension. Look, before we can even think about finding those peaks and valleys, we've got to get a handle on the landscape itself. This is where we make the leap from thinking about simple lines to these incredibly complex surfaces. Okay, think back to your first-year calculus class. You were basically hiking on a single, well-defined path, right? All you needed was the slope to know if you were going uphill or downhill. It was pretty straightforward. But now, welcome to multivariable calculus. It's like you've been dropped by a helicopter into the middle of a massive, uncharted landscape. You're not on a path anymore, you're on a surface, and there are hills, valleys, and mountain passes coming at you from every direction. So yeah, pretty obvious that a single number for slope just isn't going to cut it anymore. To navigate this kind of complexity, we need a way more advanced set of tools. And that, my friends, is exactly what Chapter 3 is all about. Which brings us to Section 2, mapping the curvature. So we're standing in this new, complex landscape. How in the world do we actually describe its shape? Well, we need the right tools. And in math, those tools are derivatives, but not the ones you're used to. The key tool we get here is the higher order derivative, and I want you to stop thinking of these as just measuring slope. Think of them more like super sophisticated surveying instruments. They're the things that tell us about the actual shape and curvature of the surface we're standing on. Here's a good way to think about it. The first derivative, that's your compass. It just points you in the steepest direction, uphill or downhill. But the second derivative, that tells you what kind of ground you're actually standing on. Is the ground curving up under your feet, like you're in a bowl or a valley? Or is it curving down away from you, like you're on top of a hill? That's the crucial difference. Okay, let's build some intuition. Just picture this. You're standing right on top of a perfectly smooth, dome-shaped hill. No matter which way you look, the ground is sloping down, away from you. That uniform downward curve is a huge clue in the math. It's basically screaming at you that you're at a local maximum, a peak. But now, what about a Pringles chip? The potato chip. It's actually the perfect real-world example of a mathematical saddle point. Think about it. If you walk along the long side, you go down and then back up. But if you turn 90 degrees and walk across the short side, you go up and then back down. The curvature is completely different depending on which way you go. This mix of up in one direction and down in another, that defines a totally different kind of critical point. Okay, on to Section 3, finding peaks and valleys. So we've got our tools, we know how to measure curvature. Now it's time to put them to work and officially start flagging the most important spots in our landscape, the extrema. So with these new tools in our back pocket, we can finally put names to these things. A maximum? That's a peak. A minimum? That's a valley. And that Pringles chip? That's our saddle point. And the best analogy for that is a mountain pass. It's the lowest point to cross a ridge, but if you're coming up from the valley on either side, it's still way, way up there. But wait, what happens if you're not allowed to just wander anywhere you want on this landscape? Imagine you're forced to stay on a specific hiking trail. The highest point you reach on that trail probably isn't the actual summit of the entire mountain, right? This is a huge concept called constrained optimization. And yeah, Marsden and Tromba have specific tools for this, like a modified second derivative test designed to solve exactly these kinds of messy, real-world problems. All right, section 4 is the physics of optimization. And this, for me, is where things get really mind-blowing. This is where all these math ideas start to reveal something incredibly profound about the universe itself. Because here's the crazy part. Finding peaks and valleys, it's not just a puzzle for math class. It actually seems to be a fundamental principle of the universe. If you look at the supplementary material in the textbook, you'll see that nature itself is constantly trying to optimize things. I mean, just take the principle of least action. It's a fancy name, but the idea is simple. Nature is lazy, or you could say it's efficient. The orbit of a planet, or the path a ray of light takes, it's not random. It always follows the one path that minimizes some combination of energy and time. Everything is a solution to some kind of cosmic optimization problem. And here's another incredible example right from the book. There's this thing called the Korteweg-de Vries equation. It describes solitons, which are these really weird, lonely waves that can travel for miles and miles without losing their shape. How do they do that? Well, the equation uses higher-order derivatives to perfectly balance the wave's curvature, which keeps it from just flattening out. That's a direct, real-world application of the exact tools we've been talking about from Chapter 3. Okay, and that brings us to our final section, the bridge to vector fields. Let's take a second to see how everything we've talked about creates a blueprint for where we're headed next on this mathematical journey. So let's just connect all the dots real quick. Chapter 3 takes the basic idea of derivatives from Chapter 2, right? It uses them to map out curvature. Then it uses that map to find critical points, the peaks and valleys. And then it shows how those findings apply to the real world of physics. This whole process, this way of thinking, is the perfect setup for what comes next, vector fields. And you can just think of vector fields as maps that show flow, like wind patterns or ocean currents or magnetic forces. And understanding them is absolutely essential if you want to get into things like fluid dynamics or electromagnetism. And hey, don't just take my word for it. As one analysis of this textbook puts it, this stuff is nothing less than the foundational language for massive fields of science and engineering. And if you want to speak that language fluently, you absolutely have to understand how to find extrema. And that, ultimately, is what makes this so powerful. It doesn't matter if you're trying to maximize profit in a business, or minimize waste in a factory, or find the most stable design for a bridge. You are looking for extrema. It's everywhere. So I'll leave you with this question. In your world, what peaks and valleys are you trying to map?